So there's 20 meters. So up here on 15 meters, it's important to tune the box just off frequency, so you're not, and with stations it's harder to tell what's going on. Okay, without the box, kind of annoying. So here's some daytime noise on 80 meters. Pretty nasty. Let's see what we can do with this. So, did improve it. About 20 dB, but not as much nulling as I would have liked. And of course that's because the antenna is probably not set up to pick up that noise as well as it should. Yeah, I need a little more gain at that frequency, so I need a bigger antenna to get a better null than this, but it's still helping quite a bit. So I know you guys are very excited about starting the project, starting the noise canceller project. I like to sketch out, what the front panel might look like. This kind of jogs my mind to see what kind of switches we might need on the front, what kind of accessories, based on other units that you've seen. Is there something that maybe you'd like to add? But the basic canceller, let's keep it very simple to start with. I think we only need 4 controls on the front box. We need the gain control and the phase adjust control, and then maybe an on-off switch, and maybe the phase flip switch. So we'll just keep it to 4 controls to get the basic noise canceller. Going to need 3 RF connectors on the back. These can be BNCs or SO239s as shown. I'm using the 239s because most of my cables have PL259 male connectors on them. Also, some type of power inlet or a grommet to run the DC power into the unit. Probably not a great idea to have a transformer in the unit. We don't need to add more noise into the box. So I'm using a wall wart 12 volt. It looks like it's a 1/2 amp wall wart. This guy came with a nice plug, that's typical. And I was able to find a jack in my junk box. So that's going to plug right into there. I'll have some polarity protection as well as a 9 volt regulator. So that's all I've mounted in the box so far. This will get me started with the prototyping boards, and we'll try to get the basic canceller started in this box. And then once we're done, we can add the fancy stuff, the additional filters, the additional amplification, things like that to the front panel. So I've got some other holes here. Doesn't matter what we do, we can always put a label on the front to cover holes. So don't be afraid to put holes in the case up front. Even before we have the circuit designed and we know exactly what we want to build, we have to figure out what features we want. What features do we want in the noise canceller? And I like to do that by kind of roughing out some of the features I want on a front panel layout. Now, I bought a whole bunch of switches, and these switches will be useful because they're double pole, double throw switches. And I have my potentiometers. I've got my output input connectors. I've got my type 43 and my high frequency toroids, which are powdered iron. And I have a wall wart here. This is a 12 volt unregulated old-fashioned wall wart. So I'll be using some type of regulator to bring that down to 9 volts to run the box. Here's some of the possible features we might want in the box. We might want a high-pass filter, basically one that cuts in at a couple megahertz and one that cuts in at 10 megahertz. Maybe, maybe not, but I put it in there. We might want a preamplifier. Preamplifier in and out. We might want a phase flip switch so that we can put a 0 and 180 flip into the phase. And we might want a switch that allows our phase adjust to be fine or coarse. At the higher frequencies, might not need as large a capacitor on our all-pass filter. So in the high range, we have a smaller capacitor. In the low range, we have a larger capacitor. So it's kind of a coarse, fine phase adjust switch. Then we have the phase and the gain controls on the end. And I think there's room for all of that on here. So why not add all of these holes, and we can see what we end up with in the end. We'll start very simple with just a phase, gain, and maybe a flip switch, and then start to add the other as we develop the circuit. So here we have the 180 degree phase shifter. I've got a 50 ohm load on the output, and I have a 6 dB pad on the input just to guarantee 50 ohms in and out. In order to achieve 50 ohms out, I did have to add a stage, an emitter follower stage with a bipolar transistor. I don't think you can see it very well, but there is a 2N2222 down in there. It's biased so that the input impedance is around 35K. And, you know, a bipolar can be made into a pretty good buffer as an emitter follower. We can try an FET, but I thought we'd start with something simple like a bipolar. And then just a simple trifilar wound transformer. Nothing fancy here. 3 identical windings twisted together. 8 turns on the core. 8 turns on the core. So I'm feeding that into the scope, both channels, both the input and the output channels. Let me get this into the tripod. And basically the generator is set for 80 meters right now. The 80 meter range, about 3.8 megahertz. There's a 50 picofarad capacitor and a 5K pot on the all-pass network. Now you can see we can get the full 180 degrees, but we do take a little bit of a amplitude change on the output. And the output is the one that's changing. I'm triggering on channel 1, which is the input. So you can see this is not a perfect phase shifter. You do get some droop in the gain. It's not drastic, it's not 6 dB, but it's at least 2 or 3 dB of change in voltage output. Now the other issue with this particular phase shifter is because it is an RC network, it's not going to work as well at low frequencies because there won't be enough capacitance. So let's drop down to 1 megahertz. Okay, now we're at 1 megahertz, and we'll try the network. And I can't quite get to 180 degrees. Maybe I'm getting, you know, 120, something like that. In order to get more, I would need to increase that capacitor value from 50 puff to maybe a 330 or a 220 or something like that. Let me just stick a 220 across this, see what happens. Yeah, see? That 220's on there now, and now I'm hitting it. Okay, so yeah, it wants a bigger capacitor at lower frequencies. So if you want to use this thing at LF or MF frequencies, you might want to make that capacitor a larger value. And of course, the corollary to this is that high frequencies, the network will respond too fast and it will be bunched all at the end of the pot. So you might try a 22 puff if you're more interested in fine-tuning up around 20-30 megahertz. You might remember that the emitter follower has a theoretical gain of 1. It's actually just, it's going to be 0.95 or something like that. But it allows you to drive a 50 ohm load, which is important because we're going to be going into a hybrid combiner. Now, if we were going to use a differential amp for a combiner, we could probably come off the all-pass network and go right into the diff amp, which is a higher impedance device, especially one made out of a pair of FETs. So you could dispose of the emitter follower possibly. But I'm going to have an emitter follower or a source follower off an FET because I want to try some of the hybrid transformer ideas with our device. So I have a 100 puff cap in there now, so that cap works just fine on 80 meters. But when you go up to a higher frequency, like I'm up around 20 meters now using the phase shifter, you can see it's giving the full 180, no problem at all. But I'm finding that the change is occurring. I'm at 3/4 of the pot now, so this is 0, half, 3/4 of the pot, and between 3/4 of the pot and full pot is where everything's occurring. So that's what happens when you have a capacitor that is too large for the all-pass network. So you would want to have a 50 puff cap there instead of a 100. And at the higher frequencies, perhaps you'd like a 22 puff cap there instead of a 56 or a 50. So let's take a look at the basic noise canceling system that we're going to put together as our first project. It's going to require on the noise channel a phase shift mechanism. We're going to have to be able to adjust the level of the noise to equal the noise that's on the main channel. So we'll need some level control, and we'll probably need some modest gain to bring the noise up to the level with our noise antenna as it is on the main antenna, because usually the noise antenna is much smaller. So we need to have a modest gain buffer, I'm going to call it. And then we finally need a differential combiner or a summer of some way to combine the two signals, either in phase or out of phase, and we can flip the phase reverse switch and make sure they're out of phase and then on to the receiver. So the goals for this design, we're going to need some type of combiner, and I'm just going to use a passive combiner on this first one. We need a very high input impedance amplifier because the all-pass phase shifter it doesn't like to have a load on it, and it won't act normal if it has a very low Z load on. And also the level will shift as well as the phase if we don't have a very high impedance that the phase shifter is seeing. But we would like a low Z output, a low impedance output, something around 50 ohms to go into the combiner. And we're going to need a little bit of gain, so maybe we should target a gain of 10, which is 20 dB in voltage terms. And I'd like to use common bipolar or field effect transistor devices rather than using some type of exotic RF amplifier or op-amp or something like that. So here is the basic schematic I came up with for this first canceller. It's using a trifilar wound toroid on number 43 core, 7 turns I've found works pretty well in the shortwave bands. If you're more interested in low frequencies, maybe put 10 turns on in the trifilar wind. Then we have a 5K potentiometer that's going to be our phase shift. There's a double pole, double throw switch that's our phase reverse switch. And we could do an all bipolar design. If you use an emitter follower, for instance, on the input, you can get upwards of 30 or 40K input impedance. It's much easier, however, if you use a field effect transistor, which is going to give you a very high input impedance and very low capacitance. Those are all good things. So we can quickly go through the amplifier. We start with the MPF 102. The MPF 102 is a RF field effect transistor N-channel. It can present several megs of input impedance and very low capacitance. These are all good things for the all-pass filter that we're using for our phase shifter. There is some gain. I have a 1 millihenry choke that I wound on another number 43 core, 43-50. That's a half-inch core. And there's a 4.7K swamping resistor across it that levels out the impedance over a wide range. I do have the source of the MPF 102 bypassed, so that's going to give some gain. I expect to get some gain through that first field effect transistor stage. I'm following that with a buffer. This is a cascade of two 2N2222s. The first stage is a standard H-biased common emitter amplifier, and it's followed by a direct coupled common collector or emitter follower stage. This common collector stage is capable of just a couple of ohms output impedance. So we have a 47 ohm resistor on the output that brings it up to 50 ohms. Now, I am kind of breaking the rules by putting the 5K pot right at the end, and that will spoil the impedance, but most of the time we're going to have the gain fairly high, and I expect the impedance to be okay going into the hybrid. This is a very simple way to do gain control. It is not proper, but it will do the job for what we're trying to do. So all in all, a fairly straightforward and simple amplifier. I've got the voltages on there. As you know, we like to have that last stage about half of the VCC. 4.5 volts will be your target voltage. I'm up at 5.5 volts, close enough. And I just measured the voltages and recorded them on the schematic for you. So that's the basic circuit. We have a little bit of gain, and I think this should be adequate with our small noise antenna, which is only really a 10-foot pole. So here's a fairly high noise level in the afternoon, and there happens to be a little bit of motor noise in there. So I'm going to engage the noise canceller. Here we go. Okay, so it's doing a pretty good job against the motor noise. Let me just remove the noise antenna completely. It's back. Now with the noise. .180 switch. 180 switch. Back in. So even when you have just a slight interference, as long as that noise antenna can hear it, you can usually cancel the noise out. So we got some annoying noise down here. 2 megahertz. This is normal for the middle of the day. Let's engage the noise antenna. Okay, the noise gets worse. Ooh, I just flipped it 180. Wow, that tuned in really nice. Again, the noise box down here. All I'm doing is, here's 180 and out. Phase adjust. Amplitude adjust. Zero. Not bad at all. So there's been some questions about my little noisemaker. This device where the relay actually excites the tuned circuit is nothing new. In fact, these types of relay oscillators, I guess you call them, have even been used to excite Tesla coils. So you're making and breaking the relay. As soon as the relay contacts come together and the coil is energized, it immediately breaks the contact supplying the power, and the spring brings the relay back, and this all happens very quickly. We're operating at about 2,000 hertz with this thing, and it's at the same time the capacitor and the coil in the tuned circuit are being energized. And of course, when you have basically a square wave feeding power into a tuned circuit, and it's producing RF pulses, much like a spark gap transmitter in the old days. And by hooking this up either to a whip, it represents the noise-making system. It's quite broad, even though it has a tuned circuit, and most of the energy is around the frequency I have it tuned to. It puts out noise merrily all up and down the shortwave band. Fortunately, it doesn't go very far. Okay, I've got the noisemaker on. That thing really puts out some raucous noise all over the band. Doesn't matter what frequency we're on, it's pretty steady. So let's turn on the box. And let's engage the noise antenna. Out, noise box in. Out, noise box in, phase control, amplitude. Yeah, it's doing the job. There's definitely a signal there. There's a station at 12.050 megahertz. Let's put the noise antenna on. There it is. I've been able to null out the noise that I'm generating with the noise box, and we can now hear the station. So here's with the box off, noise antenna disengaged, noise antenna engaged, box on. Okay, we're up in the 19 meter band. Okay, without the filter, just hearing some popcorn noise, but with the filter, it goes away. Very nice. Did you know that there are people that buy these noise canceling boxes from very reputable sources, and they will hook them up to their station, they will try them for a while, and they'll determine that these boxes don't work. I tried everything and I can't seem to figure out how to run the box. It's not canceling the noise like they said it would, and so on. And then there's folks that say, man, I should have gotten this thing 20 years ago. It's unbelievable. It's like a miracle in the shack. I can hear stations now. I never thought I'd be able to do ham radio in this QTH. And I can't believe what these boxes are doing for me. And the thing is, I believe both of them. Really, there are a lot of variables involved here to cancel noise. Even if you have the box that can do the proper phase shifting, proper summing of the signals so you can cancel that signal perfectly. You have enough gain in the system so that you can get the noise lined up with the same amplitude as the incoming signals. And still they fail. They fail to be able to get rid of the noise. A lot of it has to do with, of course this is old news to you guys, the antenna. Is the noise antenna actually picking up the offending source? So don't get discouraged if you find certain frequencies that work better than others with these boxes. We're trying to keep the part count down, but it doesn't look like we did a very good job with the amplifier because I see three pieces of ferrite. I gave you a schematic, a simple schematic of the box. We have more things to add here, and don't be afraid to build what we have here because it does work. But I will let you know that I'm not going to be religious about this circuit. If there's something that works better as we develop the circuit, I will make some changes. And stand by for the next edition of noise cancellation.